Hello wonderful people, it's Medicosis Physics Mathematics. Welcome back to my physics playlist. In previous videos we talked about an introduction to physics, how to read physics graphs. We talked about physical quantities, measuring tools, measuring units, scalars versus vectors, distance versus displacement, speed versus velocity. We talked about acceleration, we talked about force, we talked about weight versus mass, and today it's time to talk about torque. Torque is a vector, meaning it has a magnitude and a direction as well. Whenever you think of torque, you gotta think about rotation. It's a rotational movement. Torque is the product of the magnitude of the force multiplied by the lever arm, or the distance between the force applied and the fulcrum, or the pivot point. Every time you change a flat tire, you are using torque indeed. Click the like button, click the subscribe button, and let's get started. This video is part of my physics playlist. Try to watch these videos in order for maximum understanding and retention. Especially the last video on translational equilibrium, which is part of static equilibrium. Recall that if this is a box, weight is pulling it down, reaction force is trying to pull it up, the weight of this other box is pushing it this way, and this is counteracted by friction force. Recall that force is a vector. It has a magnitude and a direction. Today we're talking about torque, which is also a vector. It has a magnitude and a direction. The magnitude is represented by the length of this arrow, and the direction is depicted by the arrowhead direction. Up, down, east, west. Make sure to check out my other playlists as well. If you want me to personally tutor you, please reach me out on this website, medicosisperfectnatus.com. Physical quantities are divided into fundamental quantities and derived quantities. Fundamental are essential. They cannot be defined in terms of anything else. But derived physical quantities can be defined in terms of something else because they are derived from that thing. For example, according to Newton's second law of motion, force equals mass times acceleration, one of the most important equations ever. So force is derived from mass and from acceleration. Today we'll talk about torque, and torque is also a derived physical quantity. It is derived from force and the lever arm. Force is measured in Newton. The lever arm is a distance, so it is measured in meters. So here is Newton multiplied by meter. So how do you measure torque? Newtons times meter. Mnemonic time. New Mexico has a lot of torque. What is a scalar? A scalar is a physical quantity that has a magnitude only but no direction, such as speed, which is a scalar, mass, which is a scalar, but a vector has a magnitude and a direction, such as velocity with the v is a vector with a v, and weight with a double V is a vector with a V. Torque is also a vector. It has a magnitude and a direction. That's very important. Please don't forget that force equals mass times acceleration according to Newton's second law of motion. And don't forget that Newton's first law of motion said that the net force, the sigma, equals 0 at the end of the day. If you wish to see more physics videos in the future, please drop a car emoji in the comments. What are the types of motion? We have linear motion, such as driving your car back and forth, back and forth. And we have rotational motion. You can rotate in a circle or in an elliptical fashion. Torque is a subtype of a rotational motion. Never ever forget this. Torque is a rotation. Rotation around a pivotal point known as the fulcrum. The study of forces and torques is called dynamics. So we have statics and we have dynamics. Hence, static equilibrium and dynamic equilibrium. Equilibria, translational equilibria versus rotational equilibria. We talked about this before in the last video. Translational equilibrium creates the first condition of equilibrium, but the second condition of equilibrium has to do with rotational equilibrium. Since torque is rotation, we'll talk about the second condition of equilibrium. Do you remember Newton's first law of motion? Yup, sigma force equals 0. How about rotational equilibrium, or the second condition of equilibrium? It's not sigma force, but sigma torque eventually will equal 0. For example, if you're trying to rotate me clockwise 5x, this x is measuring unit, let's say newtons times meters, and there is another force that is trying to rotate me anti-clockwise or counterclockwise, also 5x on this side. Well, guess what? They will balance out and cancel out one another, so that at the end of the day, the sigma torque, the net rotation, is nothing. So at the end of the day, I am not rotating clockwise or counterclockwise. What does it mean that sigma force or the net force equals 0? Well, remember that force equals mass times acceleration. Remember that acceleration is delta v, change in velocity, over delta t, change in time. If net force is 0, then the net acceleration is 0. And if acceleration is 0, it probably means that delta v is 0. There is no change in velocity, so that delta v is 0, so that acceleration is 0, so that net force is 0. Now, how come delta v is 0? Well, the change in velocity is non-existent. What does that mean? How about if you're not moving at all? Yeah, that's no change in velocity. Or how about you're moving at a constant, uniform, non-zero velocity, such as driving your car at a speed of 10 kilometers per hour east, and you're not changing your velocity. Okay, so the delta v will be 0, and acceleration will be 0, and therefore the net force will be 0. Amazing. But what does it mean that sigma torque equals 0? Please recall that torque means rotation. So at the end of the day, when you sum up all of the torques, you end up with 0. What does that mean? It could mean one of two things, just like here. Either I'm not rotating at all, so that my net torque equals 0, or it could simply mean that I am rotating at a uniform angular velocity, uniform meaning constant. If you're studying for the MCAT exam, when they say that sigma torque equals 0, they usually imply that we're not rotating at all. How can this happen? Well, imagine that we have a force trying to rotate me anti-clockwise with a torque of 5 Newton meter, and another force trying to rotate me anti-clockwise or counterclockwise with an equal force, equal in magnitude, 5 Newton meter, but opposite in direction, negative instead of positive. Both of these two will equal and cancel each other out. They have the same magnitude, but the opposite direction. So the positive torque will cancel the negative torque. By the way, it is important to know that if you're trying to rotate me anti-clockwise, this gives you a positive sign for the torque. But if you're rotating clockwise, this gives you a negative sign. Some students find this hard to believe and hard to remember. So you want the clockwise to be negative and the counterclockwise or anti-clockwise to be positive? That's weird. It's not that weird if you understand what you're talking about. Draw your coordinates. Here is the x-axis and here is the y-axis. Remember that a positive angle is the angle that you make above the positive side of the x-axis. Oh, so if you're going this way, you're going 10 degrees, 20 degrees, 30 degrees, 45 degrees, 90 degrees, etc. You're going in this direction, and this is anti-clockwise. So therefore, you are positive. But if we are rotating below the x-axis like this, well, it's the opposite direction. It's got to be negative. Still difficult? Well, this angle is 30 degrees. Sine 30 is positive half. Okay, but how about if I want this 30 degrees? Well, I have to count from the positive x-axis. So we have 90 degrees here. Another 90 is 180. Another 90 is 270. Another 60 will give me 330. Now use your calculator to find out sine 330. Surprise, surprise, it is negative half, not positive half. See, physics makes so much sense once you understand what the French toast you're talking about. If this is still difficult to remember under the stressful situation of your exam, just remember the mnemonic Asia Pacific, so that the A stands for anti-clockwise, and Pacific, the P stands for positive sign. The anti is positive. We talked about the first condition of equilibrium in the last video. It means that translational equilibrium exists only when the vector sum, delta F, of all the forces equals 0. And this could happen either if the object is not moving at all, or if the object is moving at a uniform, constant, non-zero velocity. And by constant velocity, I mean constant magnitude, speed, and constant direction for that velocity. And remember, any object with constant velocity has no net force acting on it, because if the velocity is constant, the delta V, change in velocity, is 0, so acceleration is 0, so the net force is 0. But be careful, just because the net force is 0 doesn't necessarily mean that the object is motionless. It could simply mean that the object is moving at a uniform, constant, non-zero velocity. And that was the first condition of equilibrium, describing translational equilibrium. Now let's talk about the second condition of equilibrium, describing rotational equilibrium. Remember that torque means rotation. Let's go. The second condition of equilibrium. Rotational equilibrium exists only when the vector sum of all, not forces, but torques, this time, is 0. An object experiences rotational equilibrium if either it is not rotating at all or it is rotating at a constant angular velocity. To learn more about angular velocity, please check my previous video titled Circular Motion. If the object is not rotating at all, this means that the net torque is 0. So there is no net torque acting on it, because remember, torque means rotation. No rotation, no torque. However, the exact opposite is not necessarily true. Just because the net torque is 0 doesn't necessarily mean that the object is not rotating. It could simply mean that I am rotating at a constant angular velocity. See, when you keep it organized, stuff just makes sense. Unlike your teacher with his PowerPoint. You can do better than your teacher's PowerPoint. You can download these colorful, wonderful notes at medicosisperfectionalis.com. I help you learn, understand, and pass exams. In my video on vectors, we talked about multiplying a vector by a scalar and multiplying a vector by a vector. If you recall, multiplying the vector by a scalar will give us a vector every time. What is a vector? Well, it's a physical quantity that has a magnitude and a direction. One example of this is force, because force equals mass, which is a scalar, times acceleration, which is a vector. So mass times acceleration gives you a vector. Mass times acceleration will give us force. Force has a magnitude and a direction. The force could be parallel to your acceleration if you are pressing on the gas pedal or the accelerator of your car, or it could be anti-parallel, such as the friction between the surface of the road and the tires of your car, or when you slam the brakes. So we discussed vector multiplied by a scalar. Now let's talk about vector times vector. When we multiply a vector by a vector, you gotta be very careful, because sometimes the result is a scalar and sometimes the result is a vector. If the result is a scalar, we call this dot product. What do I mean by dot product? V1 times V2 times cosine theta. This is a dot product. For example, work is a scalar, is the product of multiplying force, a vector, by displacement, another vector. Here is an example of vector times vector giving me a scalar. So work equals force times distance cosine theta. Very important. However, when you multiply a vector by a vector and the result is a vector, this is not a dot product but a cross product. What do you mean by this? I mean it's gonna be sine theta, not cosine theta. Example, torque, that's a vector. It's the result of multiplying force, a vector, by lever arm, another vector. Multiplying vector by a vector gives you a vector sine theta. Don't forget, here is sine, but here is cosine. How do I remember which is which? Well, remember that you need to sign the cross, if you're Catholic, to feel victorious in your spiritual life. What an artful, sophisticated mnemonic. Another mnemonic is the vector signed a treaty with the loser. The victorious army signed a treaty with the defeated army. So vector, sine. If the result is a vector, sine theta. But if the result is a scalar, it's not sine, it is cosine. Remember that scalar has a magnitude only, no direction. So when you multiply these three things together, you get the magnitude of the scalar, and we're done because there are no directions here. But when I multiply this by this sine theta, I get a vector which has a magnitude. You can know the magnitude by doing the math and multiplying these three quantities together. But how do I know the direction? You know the direction of the resultant vector. Remember, you are victorious, so you gotta use your right hand. As in the military salute or singing the national anthem. The right hand rule, like this. V1 is here, V2 is there, therefore the resultant vector will be there. That's the right hand. Please remember that when you multiply a scalar by a scalar, well, it doesn't matter. S1 times S2 is the exact same thing as S2 times S1. But when you multiply a vector by a vector, it is non-commutative. So let's talk about torque. Again, torque is a vector. Here is a vector, here is a vector. When you multiply two vectors and get a vector, this is sine theta. The vector signed the treaty. Remember that. How do I think of torque conceptually? Well, I'm gonna give you the craziest analogy ever. Testicular torsion and ovarian torsion. What does that mean? Torsion means rotation. If this is my testicle and I suffer from testicular torsion, this testis will rotate around its axis, which is a medical emergency. Why is it an emergency? Because when it rotates around itself, the spermatic cord, which contains the blood supply of the testicle, also rotates around itself. Oh, and this can compromise the blood supply to the testicle. Without blood supply, the testicle is gone. She gone, man. She gone. It is dead. It's over. That's why this is a medical emergency, whether it's testicular torsion or ovarian torsion. Why did I tell you this? To remind you that torsion or torque means rotation. Nothing more, nothing less. Torque is a rotational movement by definition. I mean, the word tells you what it is. Torque, torsion come from the same origin. An object rotates around a fixed pivot point, such as repairing a flat tire. Look at this. What is that pivot point called? The fulcrum. Okay, how do I get torque? Well, you need to apply force at a distance from the fulcrum. The distance between the applied force and the fulcrum, here is the distance between the applied force and the fulcrum. What's that called? This is called the lever arm. Symbol lowercase r. So what can I learn from this? Well, you can learn that torque is a vector. It depends on the force applied and the distance between the applied force and the fulcrum, also known as the lever arm. And it also depends on the angle. Where is the angle here? Look, here is the lever and here is my arm. Theta is between the two. In this situation, it is a right angle, so it is 90 degrees. Sine 90 degrees equals 1. So it's simply force times lever arm multiplied by 1. Don't forget this. Here is a vector, here is a vector, here is a vector, sine theta. Torque equals applied force times lever arm, or the distance between the applied force and the fulcrum, and you multiply this by sine theta. Define theta. Theta is the angle between the force vector, which is this way, and the lever arm vector, which is that way. Between this and this, you have an angle theta. How do I remember this equation? Well, you gotta remember sine because this is a vector. So if it's a vector, it is a cross product, meaning sine theta. Remember that the vector signed a treaty with the loser. But how do I remember force times lever arm? Just say torque is for real, for real. It is for real. Force times lever arm. If you want to say lever arm times force, I'm not going to be mad at you. So you can say torque is rough. It is rough, sine theta. Or for real, sine theta. So every time you're unscrewing the nut on your car, you need to repeat ad nauseum. For real, sine theta. Or rough, sine theta. Now, if you are good at math, you will remember the sine function. Sine 0 is 0, sine 30 is half, sine 45, 0.7, sine 60, 0.9, until you hit the maximum. Sine 90 is positive 1, up here. Then you descend. Anything beyond 180 will be a negative. So let's say sine 200 will be a negative number. So what is the lowest number possible? 0. If the angle is 0, sine 0 is 0. And what is the highest possible number? This happens at 90 degrees angle. If an angle is 90 degrees, sine 90 is positive 1, which is the highest thing that you can ever reach. Which means, in order for you to be successful at loosening the nuts, your arm needs to make a 90-degree angle with the direction of the wrench that you're using. Because why? Because this is 90 degrees and sine 90 is 1, giving sine theta the maximum positive number possible. But if this angle is like 30 degrees instead of 90, well, whatever this is, you have to multiply this by half instead of 1, so your torque will decrease. So your best torque is at an angle of 90 degrees. Put differently, torque is the greatest when the force applied is perpendicular to the lever arm. Conversely, if this angle is 0, torque is 0. Which means if you're trying to pull on the nut this way, you will never unscrew that nut. You gotta be perpendicular, man. Here is the direction of the applied force, and here is the direction of the lever arm. Vector and vector. And here is theta, which is the angle between them. I want it to be 90 degrees to maximize torque. As you successfully unscrew the nut, you will find that the wrench is making a circular path like this. Now, I think if you have changed your car tires before, you have noticed that you put so much effort to trying to change one tire. Conversely, your mechanic can do it with the utmost ease. Why is this medicosis? Well, could be two things. Number one, he's stronger than you. He has been doing this forever, while you is a young, pampered snowflake. Another possibility, which is even more likely, is that his tool is longer than yours. Yours is a small tool that has to fit somewhere in the trunk of the car without taking much space. But his tool is more professional. It is longer. And you see what happens as I increase the lever arm? Torque goes up. What happens when I increase the force? Torque goes up. What happens as this angle increases from 0 to 90 degrees? Torque goes up. Beyond 90 degrees, the sine wave decreases, so the torque decreases. So the utmost torque is at 90 degrees. The work done in moving a body is defined as the force applied multiplied by the distance, known as the lever arm. For the same work, the force required to rotate the body is decreased as the lever arm increases. In other words, this long wrench is gonna make it easier for you to unscrew the same nut, given the same force. Seesaw time. Okay, remember that torque equals applied force times lever arm times sine theta. All right, here is one person sitting on the one side of the seesaw. Okay, what's force? All right, here's going to be my weight, because weight is a force. Weight equals mass times acceleration caused by gravity, m times g. Where's the lever arm? Oh, it's this distance from the fulcrum, or the pivot point, and me. For the other person, okay, what's the force? It's my weight. And what's the lever arm? It is this distance between the fulcrum and me. In order for this seesaw to be perfectly balanced, remember that force and lever arm are multiplied by one another. And I've told you before that if this remains constant and this is multiplied by that, therefore the relationship between them is inverse, which means the relation between force and lever arm is inverse. As force goes up, lever arm has to go down. Look at this. As force goes up, this is the heavier weight, lever arm has to decrease. This is the smaller distance. Conversely, as force decreases, lever arm has to increase if you want to achieve equilibrium of torque, known as rotational equilibrium. Where is theta here? Well, here is the direction of force. Remember that your weight always pulls you down. So here's the direction of your weight. Okay, where is the direction of the lever arm? This way. So between this and this, there is 90 degrees. Oh, so sine 90 is 1. So it's as if we're saying torque equals force times lever arm. Same thing here, weight and lever arm, 90 degrees, baby. This is the same concept of balancing the loads on cranes. If one side of the crane has to carry 4,000 newtons of weight, and the lever arm here is this, well, this needs to be balanced with a bigger load in a shorter distance, so that force 1 multiplied by lever arm 1 equals force 2 multiplied by lever arm 2. Again, notice that the relation between force and the lever arm is inverse, provided the same torque. So, relation between force and lever arm is inverse. The bigger the force weight, the smaller the lever arm. Conversely, the smaller the weight, the longer the lever arm. If you forget this physics equation on the job, this might end up in a calamity and you will need to file an OSHA report. God help you. Let's practice what we preach. A seesaw had two boxes. Here's the first box and second box. The first has a mass of 20 kilograms and is located at a distance 4 meters to the left of the fulcrum. The second box is 10 meters to the right of the fulcrum, but we do not know its mass. Let's assume that the seesaw is in equilibrium. What is the mass of the second box, please? Pause the video and try to solve this yourself. What's the first order of business? Keep it organized and write down what you know, okay? I know that the first mass is 20 kilograms. How about the second mass? M2 is the unknown. Amazing. I know the first lever arm, which is 4 meters, so here is R1. How about the second? The second is 10 meters, so here is R2. Okay, now what? We want to find M2. And they said what? Equilibrium. At equilibrium, torque 1 equals torque 2. And what is torque, please? I remember torque equals F(r) sine theta. The force for the first box multiplied by the lever arm for the first box, sine theta for the first box, equals the force for the second box, lever arm for the second box, and sine theta. What is theta, please? Well, theta is the angle between the weight pushing me down and this. Oh, so between this and this is 90 degrees. How about here? Also 90 degrees. And what is sine theta? It is 1. We can cancel this with this because here is 1 and 1. They cancel each other. Now, I know the R's. I know the lever arm, but I do not know the force. Well, but remember, according to Newton's second law, force equals mass times acceleration. So F equals ma. Now, what kind of force is pulling on this? It's weight. Oh, what is weight? F sub g, which is weight, is mg. Oh, mass multiplied by acceleration caused by gravity. So let's replace each force with mg. So here is m1 g r1 equals m2 g r2. We can cancel the g with the g. I know m1, I know r1, I know r2. The only unknown is m2. Let's just rearrange this equation to keep it nice and organized. The mass of the second box equal by dividing each side of the equation by r2. What do you get? I get m1 r1 over r2. Okay, what is your m1, please? m1 is 20 kilograms. And what is r1? 4. And what is r2? R2 is 10. 20 divided by 10, simplification, will give me 2. 2 times 4 is 8. So the mass of the second box is 8 kilograms, and this is the final answer. Remember that torque equals force times lever arm times sine theta. So the relation between force and lever arm is inverse. Notice that the heavier box with a bigger mass had a shorter distance. Oh, because they are inverse. Conversely, the lighter box, less mass, had a greater lever arm. And this should tell you that my answer is probably correct. Here is the same answer in more color. Please pause and review. The keyword here is equilibrium. Now here is the same problem with the same numbers, but let's imagine that they said that the seesaw has its own mass. So this device right here has its own mass. Calculate the force exerted by the fulcrum. Okay, how can we solve this? Please pause and try to do it yourself. We want the force. What is the force? The force equals mass times acceleration. Okay, fulcrum, what force? Oh, we're trying to pull everything down. So we're talking about weight. So Fg equals mg. Nice. Here's the mass, here's the acceleration caused by gravity. But what kind of mass? Is it the mass of the fulcrum alone, the mass of the first box, or the mass of the second box? The answer is all of them together. So this m equals m1 for the first box plus m2 for the second box plus m sub f for the mass of the fulcrum. What is the mass of the first box? They told us it is 20 kilogram. And for the second box, we solved this, 8 kilograms, and the mass of the fulcrum is 10 kilograms. 20 plus 10 is 30 plus 8 is 38 kilograms. This is my m. What is g? 9.8. Let's call it 10 to keep the calculation easy. So we have 38 kilograms. Multiply this by 10 meters per second squared. What do you get? 380 newtons. And this is the force exerted by the fulcrum. The trick here is to remember that the mass is the mass of the fulcrum plus all the boxes included. Same answer in color. Pause and review. You can download my physics notes, general chemistry notes, biochemistry notes, organic chemistry notes, anatomy and physiology notes, all kinds of notes at medicosisperfectionalis.com. Check out my other playlists as well. If you found this video to be helpful, please consider supporting my channel by buying me a coffee. Go to buymeacoffee.com/medicosis. Thank you. Learn about how your kidney functions, the GFR, micturition reflex, plasma clearance, what happens in the proximal tubule, loop of Henle, distal tubule, collecting ducts, etc. by downloading my kidney physiology course at medicosisperfectionalis.com. I help you learn, understand, and pass exams. There are more than 600 premium videos available on this channel when you click the join button and choose the highest tier. Please subscribe, hit the bell, smash like, support my channel on Patreon, PayPal, or Venmo. Go to my website to download my courses, notes, and cases, or if you would like me to personally tutor you. Be safe, stay happy, study hard. This is Medicosis Perfectionalis, where medicine makes perfect sense.